Okay, just a few things I forgot, last yesterday. Um, so here, like the main message was that there are a few things, that we have to take into account when selecting an offshore structure. Okay, some things are, due to the characteristics of the reservoir, due to the experience, the negotiation part of the company, but the big part depends on the marine environment. Okay, that we have to look at. And I just, went a little bit in detail how, you characterize the marine environment, and how you actually process all of that data, because the main issue there is that there is a lot of variation in the data. Okay, so you have to use, basically to characterize, you use a diagram like that. Okay, and then it will give you not a unique value representing the sea, but the range of values and what are the frequencies associated with these values. And also, here on the model, I forgot to say, remember when you have this wave, wind, and current, you have to have some sort of a model that represents the loads on the structure. Okay, and you have different models, you have drag models, you have different formulas. So you can use also software. You can use some finite element. You can also use a prototype, a scale model. If you ever go to the marine department, they have a huge pools where they use to test the like reduced scale models of platforms and vessels. But the main intention there is to find first the displacement. What will be the displacement? And you see different structures, they have different interesting or displacement that I want to focus on, and then lately to find the stresses on the structure. Mm. And based on that, you take a decision if your structure will withstand those conditions or not. Mm. But like I told you, and here I try to make a very simple and a bit poor analog of a system, but in a like on a fundamental level, from the mechanical point of view, you can see that it has a mass, so it has like an inertia. It has some spring, which is some accumulated energy that is releasing, and has some dampening, which is you have some losses, energy losses. Okay, in a very fundamental level, abstract level. And it's only to say that all of these structures, they usually have a natural, this is resonance occurs at a natural frequency. Okay, natural, what is called natural frequency. And each structure has a natural frequency, and here we have some examples. Okay, and just to say, if you're in an area where most of your waves are going to be in that frequency, then you have to stay away from it. Okay, and here I didn't say on the picture, but it's also very interesting. Okay, you have here the range of the different phenomena. Okay, wind, for example, you see is in the upper place, so it's affecting very much all the floating structures and all the heave, roll, pitch, sway. You see, wave is actually quite also wide. Okay, it goes from maybe that's 2, 3, 4 all the way to 30 seconds. That's more or less the same range that we have here. Okay, so and also something I forgot, the data. So let's put that note here. I'm going to put it, so the data, let me put here in red. So this data, wave data, is usually collected. Okay, and there are different sources, but one of them is observations. Okay, people are going on a ship and they observe and they try to give a, it's so simple like that. They try to give their impression what is the height of the wave, for example. So which are not very precise. Okay? Then you have floating. How do you write boy? It's buoy. Okay, You have buoys, then this is the most precise information we can have, and they are typically either attached to merchant ships that they traverse the Atlantic or they traverse the area that you want to analyze, um, attached to ships. Okay, sometimes you have um, data acquisition vessels that they are going on a short trip for that. So you have merchant ships, you have exploration vessels, you have also they are might be attached to shore, okay, to lighthouses. So they have different ways, and also then you have of course simulation, okay, weather simulation, weather forecast, that they using just some data, the small data gathered, they try actually to predict what will be the state of the rest. And be aware, you sometimes you might have information on one particular area, but sometimes you don't have much. Okay, depends on the amount of data you have available. So some places you have a lot of data, you have already neighboring platform that they can tell you, so you know very well because you have gathered information for a long time what will be the weather conditions there. But sometimes it's a remote area where you haven't made much, you haven't collected much data. And usually you need to have at least 2 years, okay, at least 2 years in petroleum exploration development projects, okay, at least 2 years. So the extrapolation on the set of data you have is very important, how to extrapolate that, for because you want to have this 100 years wave, okay, significant wave that I told you, and different things. So extrapolation is very important. So I'm just going to close this by saying that you can go on chapter. I try to, because the first time I taught this class was a bit confusing, and I made these notes, and I'm not think I'm improving with time. I'm making maybe making it the same confusing. So I wrote a chapter trying to summarize, and I hope it's a bit more clear. Okay, so I recommend if for you to read this page 112, and there it's like a summary of what we have discussed here with some more details. And you're going to have an exercise basically made on this process. How do you find the spectral peak of the wave signal, and then to find the significant wave height? That's an exercise, and I will be publishing it soon. Okay. So then you're going to have that question. You're going to have one about layout of subsea systems. We're going to focus it on Oscar. And then we will have one part about what we discussed today, the topic today. Again, here's something also I didn't mention, that you have different approaches. Okay, like I told you, you can make a design just for the significant wave, okay, of 100 years. And the period you have some, that's a standard that tells you, well, you have to make at least one analysis for under these conditions. Okay. But then you have all kind of short term. You can want to make sure what happens during a storm. So you want to make enough simulations for during a storm, during 3 to 6 hours. And you also want to see what happens in the long term, which might be applicable for fatigue. Okay, these structures, they will be maybe 10, 20, 30 years on the sea, a platform, for example. And then you might have some fatigue considerations on the structure. So just, I'm not going to go too much into that, but just so I'm going to copy it so you have it on the notes and you remember. But I will, suggest you to, so let's paste that on the notes of yesterday. Okay, and especially this 100-year wave, it's not important for floating structures, but for bottom supported structures, because you need to have certain, if the sea level is here and you're expecting a wave, and here you have like the lower deck, okay, and you're expecting a wave that actually will be higher than that deck. So then you will have actually, a lot of damage done to the what is on top of the what is top side. Okay, so you have to make your design such that it's higher. Okay, and some fields just know that some platforms like I was recently last year in Valhall, they, due to the reservoir extraction, they actually, you have some that they start to, you just to sink. Okay, because you are draining uh, yeah, the hydrocarbons, and then you have some sinking of the platform, and then it goes even lower. It might reach that minimum height that it has to have. Then you cannot operate that platform anymore. Okay, it's not safe to have personnel there, to have production, processing operations, nothing. Okay, so just be aware that's a very important design. How do you say? Consideration for bomb supported structures. You have to have always higher than the. I think the term is called subsidence of the soil. Okay. And let me copy that part here. These two, so you have it. We are not going to go into the calculating loads. For that we need a few more classes. But I want you to, at least that you understand how the marine environment is described, and okay, the variability of the marine environment. Okay, so let's go today, and today we're going to talk about a very important topic, which is the flow. We're going to focus mainly on the flow performance of production systems. Okay, the flow performance is important because remember, at the end, the NPV is a function of the rate that you produce. Okay, that rate might be oil, might be gas, but versus time. So this is the main factor that is going to give you revenue. And it's very important that you make up, at least you know how much you can produce, or how much you can produce, and then take a decision how I can change that production. Okay, to make analysis. If I try, we already saw that basically in a very simple way we have two ways: either plateau production, or we have decline. But we want to be able in the field development process to find if the plateau is going, when is the plateau going to end, what is going to be the maximum rate that I can get, what is the optimum plateau rate, these kind of things. Okay, so for that, that's extremely important. So the first message I want to say is that the flow performance depends on two things. Okay, depends on one thing you can see completely isolated. Okay, and you can say it's the deliverability of the reservoir. Okay, the deliverability of the formation. And this is also important because these two things I'm going to say, historically, oil companies, they are split into these two branches. Okay, and they cooperate during the development process, but not in the best way. Okay, so one of them is deliverability of the formation. You have two processes. Okay, you have first if we can decouple that, okay, that we already discussed in this tank model, we have the storability of the formation. Okay, that means basically that's the behavior of pressure versus time. Okay, depending on how much hydrocarbon you have. And then the other thing is the pressure drop in the porous media when fluids flow from the formation to the wellbore. Okay. And that falls actually under this is the discipline that many of you are taking, and that's reservoir engineering. Okay, they are very preoccupied on that, how much the well can produce, what is the pressure drop from the formation towards the wellbore, and how the pressure is going to change, saturation, everything with time. Okay, so that's one part of the equation. But then you have, so we forgot, I like to make a drawing here. So let's make a small okay, so we're going to make maybe a subsea well. Okay, we cannot keep it floating on the air, but we have to put a small platform. Okay, so we are looking now, we are saying from here, from some place where you have PR all the way to here, where we had PWF, flowing bottom hole pressure. Okay, and that's one part. But then the other part that we are neglecting is actually we have to flow against a full system. We have flow in the wells, we have flow in the flow lines, we have a commingling system that is taking that production further to the processing facilities. Okay, so that basically is flow in wells, pipelines, risers. Okay, and here we have mainly one phenomena, which is pressure and temperature drop along the system. Okay, and so here we have also, we call it this you can call it the this is sometimes called the surface production system. Okay, because it's just everything that is higher than the reservoir, at a higher elevation than the reservoir, or you can sometimes call it the production network, and we are going to cover that in a, not today, but in a class later. Okay, so these are some of the terms you use to talk about that. So I suggest and sometimes during the development plan, you just look at this part. Okay, you just look at the deliverability of the formation. You make a model, okay, of your reservoir, and there might be different ways to represent it, but you can use a reservoir simulator. Reservoir simulator, basically it's usually 3D, and you make first you discretize your formation. You use yep. Do I have to? Who doesn't know what is reservoir simulation? Don't be shy. Even though you feel surrounded by reservoir engineers that are looking at you, like, no? Okay. So reservoir simulator, you can use material balance. Okay, that is like a 1D approach where you assign to a tank. You assign kind of a one property, one pressure, pressure drop, and then you have another approach, which is the Klein curve analysis. Okay? So just to say that very early in the process, you might just use those tools to see how much your reservoir is going to produce. But in reality, like you already know, actually, we should look at the whole system. The problem of looking at the whole system is that you have to have already in place how the well is going to look like to calculate the flow in the well. Okay, you have to know how the well will look like, how the gathering system will look like, how the riser will look like, how that pressure will look like. So there are things that are at early development stages of the field, they are unknown. So it's easier for people just to neglect it. Okay, just to say I'm going to look only at that part. But I have to use, in that case, I say, so let's put that comment here, in early development stages. Um, only the reservoir model is used for production forecast. So it will be like, in our case, we'll be just looking from here to here, right? But the clue, if you want to make that, to have a good approximation, because this, so it cuts here, okay? And the reservoir simulator is using just a pressure boundary, okay? It's using just a pressure to represent the whole system. So if that pressure is too high, you are like saying that you will need a very high pressure to circulate through the system, and your rates will be very low. Okay? And if you use a very low pressure, then you're saying that the system might produce much more than what it really can produce. So really, this approach, is neglecting that part, and the validity is, how well your boundary condition is representing the rest of the system. Mm? So I'm going to have a discussion on that, but I say, just to give you the full picture, I want to talk first about, that is an interaction between these two, okay, between the production system and the reservoir system. And I'm going to give you, for that, I want to use a term called flow equilibrium. Okay. And then we can go deep into the equations. We can go deep into, how you model each part, but just the philosophy, how these two communicate and why it's important to consider it. I think at least with this concept, it will be a bit more clear. So to do that, let's make a small thinking experiment. Okay. So let's say we have a horizontal pipe with, let's say we have liquid, or we have gas, or we have a fluid, a single phase fluid. Okay, so we have here P1 and we have here P2. Okay, and we have a rate circulating through the pipe. Let me put it inside. Okay, so we have three ways. If we have that model, we have three ways. To make calculations. Okay, so the first one will be with P1 fixed. Okay, and Q, you provide the Q, you calculate P2, right? That's just, you progress along the line. Okay, you go with this pressure, and then you progress 1 meter, another meter, another meter, until you reach the end. Okay, and for that you use all kind of equations. You can use the smoothie factor. You can use whatever you like, whatever simulator you want. So I want to ask you now how that curve is going to look like. First, we're going to baptize that P2 versus Q. Okay, we're going to baptize that the available pressure at the pipe outlet. Okay, that's the pressure I have available, because I'm going from, this is a calculation upstream to downstream calculation. Okay, so let's see, for rate equals 0, what pressure should we get? P1, right? And if I start increasing the rate, what am I going to get? How the curve should look like? Is it going down? Okay, because you say the pressure 2, it will be equal to pressure 1 plus delta P, right? And when you start having flow here, remember delta P, you have two components. You have the gravitational component and then you have the friction component. Okay, so here really the elevation is the same, so you have no difference in this component is just 0, but the friction, when you start having a rate, this one becomes to be insignificant, and then P2 will be always lower than P1. Yeah, so the curve, if you believe me, goes something like that. Okay, and it might happen, you're going to have some exercise where it might happen if you choose a value of rate that is too large. Okay, you might not come to the end of the pipe, because what happens for rates greater than this Q max? Okay, let's say this is atmospheric pressure. Okay, this is 1 atmosphere, this value here. What happens if I try, when I perform my calculations, a rate which is higher than this Q max? Let's say I'm doing my calculations on a 1 meter basis. I go here, 1 meter, 1 meter. At some point, I will reach 1 atmosphere. And then maybe the next step, I'm going to get a negative pressure, which is not physically possible, right? So that tells you really that you cannot produce more than that. Okay? So in that case, I just tell you to remember it for your exercise later. You have to increase the pressure. The pressure you have is not enough to deliver that rate. That clear? That we call the available pressure at the pipe outlet. So now we have another calculating mode, which is with P2 fixed and Q, you can calculate P1. Okay, so that will be a calculation downstream to upstream calculation. Okay, so this will be a co-current with the current, and that will be counter current. Okay, you're going against the flow. So let's see here again what we have. Q, remember this one was P1 fixed, and this will be P2 fixed. So how the curve will look like? For 0, you will have simply P2, right? But then if I want to flow a higher rate than 0, what will be the pressure that I need in 1? Okay, larger. Okay, so the curve is going to go up like that. That clear? Yes? Crystal clear, no? Okay, again. So why is it going up? If you keep P2 fixed, let's say here you have a separator, okay, or here you have atmosphere, okay, pressure. If you don't circulate anything, this will be the same as atmosphere pressure, right? But now I want to circulate, let's say, 1 barrel per day of crude. So due to the friction losses, right, I will need the pressure for it to be higher than the atmospheric pressure. Yes? So that's why the pressure, if I want to produce 1 barrel, is higher. If I want to produce 1,000 barrels, will be much higher. If I want to produce 100,000 barrels, will be much higher. Okay? And you see it's the same pipe. It's only the way where you look it from. Okay? One of them, you look it from a pressure upstream fixed, and you want to calculate the downstream pressure. And the other one, you're looking at this pressure fix, the downstream pressure fix, and you want to know what happens with that pressure. But it's exactly the same pipe. Okay? And that we're going to baptize the required pressure at the pipe inlet. Okay? So that is the available pressure. If I'm flowing that rate, that's the available pressure I have at the end of the pipe, okay, at the discharge of the pipe. And if I go here, that's the pressure that I require to flow this particular rate through the pipe against P2, against that separator. And we have, another calculation where we provide P1, okay, and P2, and we calculate Q, that we are not going to use very much, okay, but that's also another option we can use. We provide the two pressures and then we calculate the rate. Now, why I'm telling you, this story? Well, you can see the production system like it's sort of a pipe, okay, like a pipe analog. You have one end here where you have separator pressure, right? And that pressure, you have some control mechanism that I write on the notes, okay? That if we look at the separator end, you have two things. You have here a pressure, and here you have a level controller, which is maybe like a floater, okay? And you have two lines, two valves that are controlled by these controllers, okay? So if the level starts going up too much, then that valve is going to open and make it go down, okay? Or if the pressure is increasing too much, that valve is going to open and is going to blow up take out some gas. So you have this control mechanism that is always making sure, it's not exactly like that, but we have a box in between. Okay, we have the control system. Okay, that is always making sure that that pressure is constant in my system. And I can only change if I come here to that box and I log and I change the set pressure. But it's not something I can do very easily. So in that way, that pressure is a bound, okay, in which the pressure is fixed. And now if you go and see where is the pressure kept constant in the rest of the system, the other point is this reservoir pressure, right? That's the other point where I have my pressure fixed. And it's going to, so PR is a function of time, okay? But it will change very slowly. If you see at one particular point in time, let's say today, that pressure you can assume is practically constant, okay? It doesn't change. Then if you look at your system in 1 month, it might change, have a different value, but you can make your analysis at that particular point in time with a fixed reservoir pressure, okay? It's not that instantaneously, if you start draining 1 million barrels or 1,000 barrels, that's going to drop dramatically in that time. Okay, it's only going to do it in a long period of time after you have already drained significant reserves. Yes? So if you, let's say here you're circulating 1 barrel, 100,000 or 10,000, that pressure will remain the same. It will only change after you let significant amount of time pass. Yes? Okay, so in that sense, it's also a constant pressure boundary. So let's go again to our system. So the same principle, okay, the same curves can be used to characterize the production system. Okay, parts, we can say, well, parts of the production system, okay? So let's look, for example, at just, again, let's make our okay, let's look first just at the well, okay, and remove. So if you, let's say you take, here we have our formation. Okay, we have certain PR, that's my boundary condition, that is a function of time, okay, but it's my boundary condition. If I say I want to calculate going from here, I want to calculate that pressure, how that pressure will look like depending on the rate, okay, without, taking away everything else. Let's put this in a different color. Let's put this in maybe this, okay. So I go here and I say, without looking at anything else downstream, I'm going just to take the reservoir, from reservoir pressure, which is a fixed pressure bound, all the way to the bottom hole, okay? How that curve will look like. Okay, Q can be oil, can be gas, okay, whatever I'm producing. And here I want to see how my PWF will look like. Which mode is it? The ones that we have discussed before. Is it mode 1 or mode 2? Mode 1, okay? I have a constant pressure at the inlet, okay? And then I go co-current and I calculate at the end the pressure at the outlet. In that case, my system is just the reservoir. So how should it look like? We assume, okay? We are not sure, but we assume if the pipe analog applies that it's going to look something like that, okay? So for, how do we call this curve? IPR, okay? Inflow performance. That's, IPR, petrol production, reservoir engineers like to use very much, and they call it inflow performance relationship, okay? IPR. And it tells you if I put this pressure, okay, PWF asterisk, at the wellbore, if I fix somehow magically that pressure, I'm going to get that rate, okay? And this rate, remember, this is, here we're talking, any rate. It could be standard conditions or not, but in production systems, we like to work with standard conditions rate, okay? That's because that's the value doesn't change along the system. That clear? Yeah. Okay, so let's take a break. Yeah, let's say 15 minutes, and we continue, with the rest. Just, I want to ask you, what happens if, for some reason, the pressure that we fix, in this simple example, the pressure that we fix at the inlet of the pipe is higher? How the curve will look like? Okay, it will be just scaled up, okay, in a very simple way. If the pressure one is higher, so then it will just look something, let's put a color, okay, look something like that. Okay, we'll scale up. And if we change, so that's for a pressure higher, or if you discharge pressure, let's say for some reason the separator pressure is increased, okay, then the pressure will look something like that, will be scaled up. Okay? Maybe the curves will be slightly different, but you will have a shifting. The main consequence of changing the pressure level is basically the scaling of the shifting and scaling of the curve. Okay, so we were looking at the reservoir side, and we defined, something that you already knew before, which is the inflow performance relationship. That for oil wells, you know that it looks for oil wells, undersaturated oil wells. Okay, wells which are flowing pure liquid, then that is something like this. Okay, PR minus PWF. It's actually not a curve, but it's a straight line. If you talk about gas, for gas, dry gas, okay, we have different equations, but one of the equations that we normally use, low pressure, we have something like this: Q gas C PR squared minus PWF squared to the power of n. Okay, which looks exactly like that curve. Now let's go a bit forward and let's see downstream, and let's see now to calculate the wellhead pressure. Okay, now let's say the system that we are looking at. Okay, we have here a reservoir pressure. Here we have our tubing, and here we have our wellhead, and there we have here. Okay, and the rest of the system I take it out. Okay, I don't look at the pipe, at the separator. I just look here at this PWH. Okay, or to make something to let's do something else. So here I'm going to put the choke. Okay, that's the symbol of a choke, and I'm going to make it adjustable. Okay, and I want to calculate the pressure downstream the choke. Okay, pressure DC. So how that pressure is going to look like, Q, remember oil, or Q gas, and here I have PDC. How that curve is going to look like? Again, exactly which is it? Which one? So you have to think, is it the available pressure or is it the required pressure? I'm going with the flow. Okay, I'm going, this is my constant pressure bound, and I'm going with the flow all the way to the wellhead. Okay, so in that case, I'm still in mode 1. Okay, and still the curve should look like that. If I increase the rate, I will get lower and lower and lower pressure. Now I ask you, what happens? So let's say this is for choke opening is 100%. Okay, what happens if I start now? I close the choke to 80%. How the curve will look like? Okay, first I ask you, if I have no flow, the starting point, does it change or not? This is for flow equals 0. Okay, so I have no flow, really the choke doesn't do anything. Okay, if we look at the choke, okay, we say it's one of these bean chokes that I discussed some time ago. Okay, you have PDC and PUC, upstream the choke and downstream the choke, they are going to be just the same. Doesn't do any change, right? So the starting point will be the same. But now I'm going to ask you, if I have a certain rate, Q star, okay? If I have an open choke, I will get this pressure, okay? This PDC star. And now if I close it 20% or 80%, how that pressure should be? Should it be higher than that or should it be lower than that? Okay? To help you decide, so let's see, PW PDC is equal to PR, right? Minus the delta P that's in the reservoir, minus the delta P in the tubing, okay, the flow in the tubing, and minus the delta P in the choke, right? Is that correct? That's how I do it, right? I go from here, minus this one, and minus the choke. Okay, if this is fully open, then this one will be 0, okay, for 100% choke opening, delta P of the choke, 0, and then PDC is just PR minus delta P minus delta P of the tube, right? But if I have for 80% choke opening, then delta P choke is different than 0, right? So that means that PDC is actually going to be the full expression. Okay, if the rate is the same, okay, then this one should be the same as this one, right? The delta P in the reservoir is the same, right? Then the delta P on the tubing is also the same. But I have now this extra. So the pressure downstream the choke should be lower, right? Should be lower, which makes sense. When I'm closing the choke, actually I have an additional pressure drop, and the pressure available at the wellhead is actually lower. So the curve looks something like that. Okay? That clear? Okay, so now let's look, that we look at, so that curve we call the wellhead performance relationship. Okay, sometimes abbreviated WPR, and is the available pressure. Remember, available. I'm calculating co-current pressure at wellhead. Okay, now let's look at the rest of the system. We want to look now at some, that I have the mode 2. Okay, so I'm going to look at this transportation pipe that I have, the separator, and I have here, okay, and I'm going to move now. The point I'm going to choose is the separator, okay, and I'm going to move counter current, and I will calculate the pressure, let's say PDC, okay, this pressure downstream the choke, okay. So how it will look like? How that will that pressure look like versus rate? From separator all the way to DC versus Q oil, Q gas, whatever I'm producing in my system. Okay, that's exactly mode 2, right? I'm fixing the outlet of the pipe, and then I'm calculating the inlet of the pipe. Okay, so that will be the required pressure at choke discharge, okay, or we can say at pipeline inlet. Okay, and it's going to look, let's say it will look like that, okay, going up with rate. We will see now the curves. We're going to work later on with equations, so you will see this is just like like a thinking experiment that really helps you when after you're just submerged with equations, okay, that you have to solve the actual equations. I hope this is like an experiment that helps you to so it looks like that, right? But now I ask you, how was the first experiment we made, that we went from reservoir pressure all the way to PDC? How the curve looked like? Okay, we just did it, right? Going down like that. So I ask you, is it possible that the two curves have different pressure values? Is that possible? They are exactly in the same place, okay? One of them, I'm just calculating it from here, but the other one, I'm calculating it from here, but they actually in exactly the same place. Okay, so the pressure should be the same. So when you see that, that's exactly the concept of flow equilibrium. The only point where they are the same is in the intersection. Okay, so that tells you that the system, if you put these two together, okay, if you put this pipe together with this pipe, so here I'm representing this side together with this reservoir and well, they're going to be producing at this equilibrium rate, nothing else, only that point, because I have just one intersection. Yeah, that clear? Okay, so how do I change the equilibrium point? Remember, in production scheduling, we are very much preoccupied about, changing. I don't want to be producing just at what it gives me, okay, at maximum rate. Okay, I want to be changing that rate. So how do I control that intersection? Okay, I'm going to ask you, can I make something here to control that intersection? Hmm? To control, so why? So how do I make, for example, the curve to look more like that? Okay, let's say, okay, or more like that. How do I make the curve to go like that? You can change or modify the choke. Yeah. Okay, but we are now looking. The choke is not in this system. Okay, it's in the other system, in the curve that looks like that. That curve will change with the GR as well. This curve will change with let's say with the diameter, right? If I use phi1, phi2, and phi3, and I say phi1 is smaller than phi2, smaller than phi3, then I can move the point to the left, right? If I change separator pressure, what will be the effect on this curve? Capacity of... Well, the same effect that we were discussing before, right? The separator pressure is just shifting it up or down. right? Shifting separator pressure will do something like that. So let's say, to not make a mess, this is P separator 1, P separator 2, P separator 3, and P separator 1 is greater than P separator 2 is greater than P separator 3. But these are things that you cannot use to regulate, right? You can use to decide on your rate initially, but after that you cannot use, let's say you want to have a rate which is slightly lower, you cannot go and change separator pressure, or you cannot go and change a pipe. That will be an extremely high cost. So for that we need something else on the system that can help me to regulate and that something is that guy here, this choke. Okay, is actually, let's make another curve, okay? Because I think now we have too many things on the same diagram. Okay, so remember, what was the effect of the choke? This is 100% opening, 80% opening. Okay, then you had 50%, for example, 20%. So that's how you reduce the rate. Okay, just by changing the choke, that's going to change your available pressure curve, and that's going to move the intersection of the system. Okay, that clear? Yeah. Okay, if that is clear, let's make another experiment. Okay, you will see it's like, but I hope this helps at a later stage. Now let's make an experiment where I'm plotting. So I'm going to remove the choke from the system. Actually, I'm going to assume open choke, right? And here I'm going to make a plot again of Q, and I'm going to plot first the wellhead pressure, okay, calculated from the reservoir all the way to the wellhead. How that curve is going to look like that, right? The available pressure curve. And now I want to calculate, so that will be PWH, right? And now I want to calculate the same pressure, because now I have no choke, but calculate it from the separator all the way, okay, where the choke is supposed to be. And that curve looks something like that, okay? This is available, and this is P wellhead required. If I want to put a choke exactly on that intersection point, right? Exactly there. If I want to put a choke and I want to produce that rate, okay, what will be the delta P that the choke has to provide to get that rate? Just the difference, right? Is that clear for all of you? Yeah, it's just the difference, because these two curves that tells you I have more energy than what I need. So I need somehow some element to dissipate that energy, to break that energy, bring it down to this level, to this value. Okay, so I need my choke. This has to be the delta P of my choke. And you see there are two complete different approaches. Okay, one here, we were including the choke model in my available and required, right? We were including the choke model here. And by changing it, we had to change the whole curve. In this approach, we took the choke out of the picture, out of the two curves. Okay, but now I'm saying at the intersection, if I had a choke, then this will be the delta P that the choke has to bring down to produce exactly that rate. Exactly the same, okay, the analysis has the same purpose, but is done in two different ways. Okay, and one of them, you have to think, this is already when you have a system that you have already selected a choke model, you know already how it performs, you already know these characteristics, and you can very easily calculate that curve. And this is very useful for the design phase. If you're selecting a choke, you say, I'm not sure what choke, how, the orifice, anything. The only thing I know is that this choke has to give me this delta P for that rate. And then I go to the manufacturer and I find a choke that is suitable for that. Okay? So you see the two, the two ways of thinking. So this is useful for when you perform. So this analysis is useful for performance evaluation and this analysis is useful for the design phase. Okay, when I want to select a choke. Also, what happens if I want to produce a rate which is higher than the equilibrium rate? Can I do it? No? Are you sure? Yeah. We have to use, if I want to produce a rate, let's say the rate that is here. Okay, that's the equilibrium rate. Then that's the rate with the choke. But let's say I want to produce more. For some reason, my economical rate, I found this field will not fly unless I produce this rate minimum. I made my NPV calculation and I say at least I have to produce that rate for it to be profitable.
Change tubing size, decide.
Yeah, but you want something, remember, what is the tubing size going to make? Huh? The tubing size is going to change this curve, right? It's going to make it like that, okay? But let's say it's like that. I still don't get, and it's not something that I can regulate. So an option is to put a compressor, something that will take the available pressure up, bridge it, and bring it equal to the required pressure. So I need a compressor that will give me exactly this delta P for that rate. Okay? So that will be delta P of a compressor. Can I here design, for example, with these two curves, a well with an ESP, with an electric submersible pump? I can, but I have to change the equilibrium point. Okay? Because now we are looking at this position. We are saying like if we are going to install a compressor or we are going to install a choke here, right? But if the pump usually is installed here, the ESP. So I have to move and I have to calculate the required curve to this point and the available curve on that point. And there I can say exactly that's the delta P my ESP needs. Okay? So I have to move, remember, and that has to be for this type of analysis. Let's make, so this is the design type analysis. The equilibrium point must be at the location of the equipment. Okay, and keep that in mind. You cannot make, if you want to make this type of analysis, you have to put it exactly where the equipment is. So now let's look at the, the last part of the class. I want to talk about the effect of depletion. Okay, effect. Okay, so time effect. So for that, let's take again, you're going to get tired of drawing wells in your notebook. Again, let's take the single well example. Put the separator here. And here we have P reservoir. Okay, and I'm going to choose my equilibrium point. Let's say there is no choke anything to make it simple. I'm going to take my equilibrium point at the bottom hole. Okay, and I'm going to plot the available curve. Okay, that we said this was the IPR, right? And the required curve, which, how is it going to look like? Just like that. right? So what will change with depletion? Reservoir pressure will go down, right? Okay. So where do we have reservoir pressure here in this plot? This one here, right? This point here is exactly reservoir pressure 1. With depletion, what will happen is that this curve, the deliverability of the formation, if we use QO, this equation, right, for liquid, this number will go down, okay? So then it will give you less rate. The curve will do something like that, okay? So then the equilibrium rate will be reduced in that manner. That clear? No big surprise there. So the available curve is the one that changes, and it's mainly because of the reservoir pressure decline. Now, should we attempt to do the same experiment now with the choke? Okay, now let's put again a system with depletion and the choke. With depletion and adjustable choke. Okay, so let's make again our system. Again, we have here reservoir pressure, and remember we had P, we call that's pressure and rate, and we're going to put one plot which will be the pressure at the wellhead, and then we have another curve which will be the pressure downstream the choke. Okay, so which curve is going to change with depletion? PWH, right? How is it going to look like? Exactly the same, a similar trend like this one, right? Remember, this curve is only delta P in the reservoir. Now, this curve here has delta P in the reservoir plus the delta P in the tubing. Okay, be aware of that. So you have two phenomena happening there. That equation is a reservoir flow equation and has a pipe flow equation. Okay, but with time, due to the decline in reservoir pressure, that curve actually will go down. Okay, so that will tell you that in principle, if I leave the choke, if the system has no choke, that will be the rates that I will produce. Okay, now I ask you, let's say we are producing our field in plateau mode. Okay, and let's say I decide for some reason my plateau rate has to be this rate, Q plateau. According to this diagram, what do I have to do first? In year, let's say here this is time 1, time 2, time 3, time 4. What do I have to do in time 1? I have to put a choke, right? Because I don't want to, in time 1, if I put no choke, open choke, I will find this rate, right? The system itself, it will equalize. Equilibrium nature is like that. It will equalize in that rate. I want really to produce this rate here. Okay, so what I have to do, I have to put a choke that will bridge that difference. That will be the choke in year 1. Delta P choke in T1. For year 2, exactly the same, but now my choke will be this one, right? And this will be delta P of choke for T2. And now for T3, actually, yeah, in T3, the available pressure is less than the required. So that means naturally the system cannot produce that rate unless I help it somehow. Okay, unless I put a compressor, unless I put something to boost the difference. So if I don't do anything, if I have only the choke at that point, then the system will enter into decline. Okay, so if we plot here the rate, right? If we plot here Q, Q of the well. Okay, we're talking now a single well system versus time. For time one, you will have Q plateau. Time two, you will also have Q plateau. But what will happen in time three if you don't install anything? Decline. Okay, so here you will have Q3, and here you will have Q4. Okay, and there you managed to find your production profile for how long you will be able to produce that QP by taking into account the effect of the two things of reservoir and production system, and assuming that you're controlling with the choke. If I go back to my manager and I say, well, your field will be able to produce for 4 years and then it will decline, and I say, no, we have a contract, we have to deliver for 5 years. So then you have to make a plan to install either a compressor, or you have to change this curve such that the intersection gives you more to the right. Okay, and for that you might change the tubing size, you might change the pipeline size, you might lower the separator pressure, but you have to do something such that the intersection will be shifted to the right. Yes. Okay. Okay. So I think at this point will be nice to have an exercise, but I think we are going to. What do you think we leave it for Monday? Or you want to have an exercise now? You don't want to be. No, just be honest. No? Okay, so let's make an exercise. So we will have. We are going to have use some equations. Okay, so in next class. Um, um, yeah, just wait a moment. Let me check something here. Yeah, we will talk about networks later. Okay. Yeah, maybe I can make a small comment on that. Okay. Um, so just sometimes, so you say when the flow is multi-phase. Okay, that means, and that normally happens when you have, for example, with you are transporting gas, you always have some liquid dropping out of the gas, either water or condensate. Or when you have oil, you have just the vaporization of the gas in the oil. Okay, so that will be gas plus liquid. Okay, or if you have oil plus gas, okay, plus water. Okay, the we can call it a pressure curve looks slightly different. Okay, and I'm going to again to see exactly what we are looking at. So we are looking at okay PWF H, and I want to calculate PW. This one is fixed, and I want to calculate PWF versus Q. So like we already said, that you have just the friction that you had just the friction part, right? So that's why it looked like that. That's for basically for single phase system, single phase gas or single phase liquid. But when you have multi-phase, something actually very strange happens, that you have a behavior which looks something like that. Okay, going down for low rates and then it starts to go up. And that causes that basically you have, if you have the available pressure, right, you have your IPR from the reservoir, that you have two intersections. And that can happen for any system that you have more than one phase. So what happens in that case? Can the system operate at the 2 points? Doesn't make any difference. For that, there are some you can find some in mathematics. That's called, you have to make a stability analysis of the solution. Okay, you have to see if the solution is stable. If I have any fluctuation of pressure or rate, and then the solution might change, okay, might go to another point. But I want to make it a bit intuitive. So say, let's look at this solution here, right? And I have here my equilibrium rate that I call 1. If for some reason there is a perturbation and the rate is higher, okay, the rate is thrown to the right, what will happen? The required pressure is bigger than the available, right? So what does it make to the system? That I have to reduce the rate, right? Because the available is less than the required. That means that I have to reduce the rate. That means that it tends it to just to balance it, okay, to return to the equilibrium point. If I make a change on this side, okay, what will happen here? The available is more than the required. So then that means I have to increase the rate. And again, I'm pushed to the equilibrium rate. So it doesn't matter, this point is very stable. Doesn't matter if there are any changes, it will always stay around the same point. If you want to make a mechanical analog, it will be something like that. No matter where you put the ball, it will always end up in the center. Now what happens to that point that I have here? If I'm operating at that rate, right, and then I make a small change to the right, the available is more than the required. Then I have to increase the rate. Then I increase the rate, the available is still more than the required, I have to increase the rate. So it will end up in this point. Okay, and if I move it to the left, then the required is more than the available, I have to reduce the rate, reduce until the well is not producing, shut in. So this is an unstable equilibrium point. And if you want to make a mechanical analog, it will be like something like this. Okay, if you move it slightly out of its operation range, it will just move either to the stable point or either to 0. And these wells, it might be a bit difficult to start up just because of that. When you're starting to start up the well, it goes and closes. Then you move it again, try to produce, it goes back and closes. So you have to give it the rate, to the startup rate has to be high enough such that you are like where the available is more than the required. Okay. So now why we have this curve? Why is going down and then up? That I already said, is for multi-phase, but in a very simplistic way, what is happening is for these low speeds, if we see yeah, I prefer leaving that for next class. I think you're tired, and so next class we will go very briefly why it looks like that in multi-phase. I will give you like a simplistic explanation. Those of you taking the course with Nidal might give also some input. But then next class we're going to put actually numbers and equations to all of these caricatures we have made and try to actually compute some numbers. Okay, so next class I will try to make a group activity where, and the activity will be part of the second exercise set that you have to deliver. Okay, before we close, any question? No, everything crystal clear. Yeah, like that. Okay, simplistic, like some questions during the break saying that why if we have a pipe going downwards, then the curve will look slightly different. Yes, but this is an approximation. It might be very different if the pipe is not horizontal, might be a bit look slightly different for depending on the conditions of the system. But basically, you always have an available pressure that ultimately is going down with rate, and you have a required pressure that ultimately is going up with rate. And the intersection, the equilibrium point, is when the two are the same. And you can make one type of analysis saying including the equipment. For that, you need to have a model for the choke. You need to see how the opening affects the delta P. And you can make another type of analysis that is something we're going to use very much in this course, just taking it away. Because at early phase, we don't know exactly all the characteristics of this component. So we take it away and we say, if you had a compressor or if you had a choke, what do you need, to make it work, to produce the rate that you want. Okay, see you on Monday. Have a nice week.